Okay, so let's start. So the last time we understood more or less that the Hilbert space of any conformal field theory is a direct sum of modules of Virasoro algebra. So actually, these modules can be different if this dimension is special. So it can be either the full Rama module uh, uh, or something reduced. And now let us talk a little bit about this. So but all of them are highest weight representations in the sense they have some vector of dimension delta, which is killed by all positive generators. So, namely, we have some vector on which this L0 x by the eigenvalue, um, and L was n greater than 0 x by 0. And if you want to construct some representation starting from this vector, we can basically take all Virasoro generators and act on it. So we can construct the object which is called Rama module. Which is a span of all vectors of the form L minus n1. So L minus nk acting on delta. And with n1 greater or equal and so on greater or equal than nk. And such vectors can be labeled by the Young diagrams, namely the first row has length n1, the second row has length n2, and so on, some nk. And the question, what is the eigenvalue of L0 acting on such vector? Maybe. Of what? And what else? I can write in commutation relations in the Virasoro algebra. Mm. What is here? Mm-hmm. Times or plus? Mm-hmm. Yes, thanks. Acting on the state. So in this description, it is the number of boxes in this young diagram. Mm. And we have already seen such example. It was for the free boson where the Hilbert space was described not as a representation of the Virasoro algebra, but as a representation of the free boson algebra. Let me check. Thank you. So this L0 is a very natural gradient operator, and if mm, if we write vectors in this module according to their gradients, it will look like this. So it will be this highest weight, then there will be L minus 1 delta, and there will be L minus 1 squared delta, L minus 2 delta, and then 3 such vectors, and so on. And people draw it like this. Mm. Oh, and if we ask about dimensions of representations of Virasoro algebra or of some other algebra of this kind, and the algebra that has some integer index, so it makes sense to ask not about the dimension of representation because it is infinite dimensional, but about its character. So namely, we'll compute characters of this V of C delta, and character is a trace of Q to L0 computed on the space. On what do you think? What does it equal to if we suppose that all these vectors are independent, that we don't factorize this module over any submodules. We just take all such vectors. So. Hmm? What is geometric series? Hmm. Mm-hmm. Well, we can write it like this: q, but to which n? Q to the n. How to write this? Hmm. No, we have no, we can act with L minus 1 squared, for example. So this one is just a point, this one is a single box, this one is this diagram, this one is this diagram. Oh, the point is that this else can be, so if you have some monomial in else with negative indices, we can use this commutation relation that indicates the overall power in L and reorder them in this order, so in decreasing order. And then it is identified with the Venn diagram. Yeah. So the question is how to compute. We can ask about the numbers of such vectors for each eigenvalue of O0, and this will be sum with the number of partitions, like p of n q to the power n. But it does not help much because there is no formula for the number of partitions, and even if we knew some formula, there would still be a problem to compute this sum. But how to compute it without such knowledge? Yes, we can. So they will will not be ordered, but we can do this. Like we can say that this v let's see, delta is a span of the infinite product from n from k equals to 1 to infinity L minus k to power mk. Yeah. And so what kind of answer does it produce in this representation? Sum over k or uh, or hmm? Oh, hmm? K is an index. So I would say that it is sum over all m's, m1 and so on, from 0 to infinity. Yes, q to sum of k and k. Right? Hmm? Hmm? Below? So it's a sum over all m's. So m1 equals to 0 to infinity, m2 equals to 0 to infinity.
And then we multiply by the sum of the partitions.
Sorry. Equals to q to the delta. Yes. So we just list all such states. And, and now we can compute this sum. Right? So, right? And uh, and also so they want to say we can also interpret this sum and this phrase as a partition function on a torus. So with a modular parameter q. So it can be also written as drawn as a the annulus of with two idea, one an absolute value of q, and with the identification z is equivalent to z times q. So this trace is a partition function on this torus, and if you look at this answer, we can see that it is mm, q to minus 1 over 12 q to delta q to 1 over 12 divided by the Dedekind eta. Right? So it suggests that such characters usually have some clear modular properties. So we see it from the answer that it contains the Dedekind eta, which is a modular form, and we can also guess it from construction, because a trace of q to 0 is this partition function. Partition function can be computed in at least in two different ways. We can cut the stores along the A cycle and along the B cycle. And we can also choose the B cycle up to some addition of A cycle. So there is this modular group that acts on such objects. And this 1 over 12 is also not a coincidence. It comes from this correction when we go from a cylinder to torus. It comes from Schwarzschild derivative. So actually, the correct partition function should contain this shift of LZR. But maybe let's not go into the detail. I just wanted to say that all this is not a coincidence. Mm. Yes, so we have this character, and now if you see some other representation, and we want to express it as some combination of Virasoro modules, we can just compute its character, and if you know that it is a sum of irreducible Virasoro modules, then just divide by Virasoro character. Uh, so, for example, we have this this Fock space for the free boson that corresponds to arbitrary charge. In the sense that it is j minus n1, j minus nk, a span of such vectors. J0 acting on alpha equals to J0 acting on alpha equals to alpha. And we can compute the character of this representation in the same way. So it will be q to alpha squared over 2 because it is the dimension of this vertex operator. Divided by product of 1 minus q to the k. So and we know that Virasoro algebra also acts here. So comparing these two characters, we conclude that this H alpha is isomorphic to Virasoro Verma module. So it happens actually only for generic alpha. Because for non-generic alpha, you'll see that something interesting happens here. But in general situation, we see that dimensions of this space is in each gradient is the same. So there is no other option. So if such representations are irreducible, then we have one such representation growing from this highest vector, and there is nothing else.
Sorry, what about, we say that, so delta is alpha squared over 2, then there is, shouldn't it be equal to the 1 over 12?
No, q to the 1 over 12 was added just to write the kind eta.
And that, so that is B C alpha squared over 2 or B1?
Yes, so C.
Why you take 1? Because we are in the theory of 1, well, C is 1.
Yes.
Okay.
Yes. Yes. So to know this, we need to know that these modules are reducible, but we will understand this later. Yes. Oh, except for let me think. Except for mm, so except the latest 1 over a square root of 2 times integer. So there will be points where this Rama module becomes degenerate, and in this case, this Fock space will consist of many irreducible Virasoro modules, which are factors of this Rama module by some submodules. Oh, Virasoro algebra, let us discuss it now. So Virasoro algebra, in principle, can have different representations. So the most naive way to construct some representation is to construct this Rama module. In a sense, just take some highest weight vector. We will always have this because dimensions of physical states are restricted from below. So we should have this highest weight vectors, and once we have it, we know that all positive modes act by zero. The action is already defined, and we define the action of all negative modes, saying just that all such states are the new independent states. And action of the Virasoro algebra on such vectors is well defined, because if we add with a negative mode, we just pull it through the other else and place in this order. If we act with positive mode, we just compute all these commutators, rearrange them, and we again get a state from this vector space. So we can get a linear combination of such states. So it means that there is a map from this Varma module to a representation of Virasoro algebra. So how to say it? So suppose that we have some H representation of the Virasoro algebra. There is some vector delta in H such that Lk greater than 0 on delta equal act by 0, L0 acting on delta equals to delta. So if it is true, then uh, then there is a map. I don't know how to call this. Some well, let me just write in words. So this map sends delta from from this Verma module to delta in the Hilbert space. Then, of course, there are questions. For example, can this map, well, maybe, mm, maybe let us write some name. Hmm? It depends because in principle this map can have kernel. So because if uh, mm, because if this module is irreducible, oh, so it is clear that a kernel of M is another representation. So so it is some a submodule in this Varma module, and the only question is if it has some modules at all, because so if it contains some submodule, then we can just send this submodule to zero, in a sense factorize by it, and get a map to, for example, a reducible representation. So it can happen, and it happens like in special situations. Mm. Yes, it's not true. In general, it is some of some representation, some representations of the Virasoro algebra. So it is true only for generic dimensions. Mm. So it is some representation of Virasoro, models of Virasoro. So let us try to think about about possible structure of this Varma modules. Mm. And so the representations are basically Varma modules factorized by some submodules. Which can be either just Varma modules or something more complicated. Like they can also be Varma modules factorized by something. Uh, so So let us start from the first non-trivial vector in this module. So we have delta O minus 1 delta and everything else. And so if this module has some submodule, it means that this submodule should have some highest vector. If this highest vector is the original one, then it means that we get our original representation. So so it should be some different highest vector. Okay, probably better to do like this. So let us ask, what happens if this vector is just in the first non-trivial component, so of non-trivial weight? So what should we check? So what is non-trivial about this vector? So is it clear that all L's starting from 2 act by 0? So Lk greater than 2 and L minus 1 delta act by 0. So the question, so it's eigenvector of L0. There is no such question. So we should check what happens for L1. So L1, L minus 1, acting on delta, gives 2L0 acting on delta. So when L equals to 0, so when delta equals to 0, we see that L greater than 0 acting on this L minus 1 delta equal to 0. Oh, sorry, what did I write? When delta equals to 0, so this is it fine? Okay, but so this we see. So there is a map from we see one. Maybe let me write it explicitly. So acting on L minus 1 vacuum is in this VC0. So actually for a generic central charge it is an inclusion. So for generic central charge this one is irreducible. This so this is VC1. This VC1 is irreducible. Yes, because this condition about reducibility is a condition on dimension of central charge, and if we found one highest vectors somewhere, we used one such condition, and if there is central charge, in principle, we can get highest vectors somewhere else. So there will be some discrete set of points in C, and on this condition that we have two highest vectors somewhere is a condition of minimal model. But in general situation, we have just one. So and yes, yes. So in general situation, it is an inclusion. So and if we want to construct some irreducible representation of Virasoro, we need to just factorize this by this. So and it is called a vacuum model. I don't know if there is some name for this, maybe vacuum. Will be VC0 factor by VC1.
Which corresponds to the image under small n of
VC0. Of VC1. Because it is some highest vector that has dimension 1. It is generated by L minus 1.
So I need VC0 and take it to under n by not n bar.
So you mean that so in a sense MVAC, this whole module is an image of this V. Yes, but it is always the same. It is just the definition of vacuum module that it is a irreducible module that contains a field of dimension 0. And we can compute the character of this module. So for generic central charge, can you tell me the answer? So there are kind of two ways to compute this. If you know that there is an inclusion of this form, so this image does not have a kernel. So there is an exact sequence. So, hmm. So there is 0, VC1, VC0, M vacuum, maybe with central charge C. So a character of this is just a difference of these two characters. So it is the difference of 1 over product 1 minus q to the k from k equals to 1 to infinity minus q over product of 1 minus q to the k from k equals 1 to infinity. So it is just 1 over product of product from k equals to 2 to infinity. 1 minus q to the k. Right? So so it is for a generic central charge. And let us try to think about this result from the point of view of operator state correspondence. And also about the fact that we have a highest vector L minus 1, and we need to factorize over this subrepresentation. So the first question is the following. So suppose that we have some state that corresponds to operator O. So some state O maps to let us say that let us use this this vertex operator algebra map. So some state V in the Hilbert space corresponds to some operator OV of Z. OV. So the question, what corresponds to the state L minus 1 V? So how to define the action of the Virasoro algebra at point Z? So we can write that it is L minus 1 O V of Z. But what is the definition of this action of Virasoro in terms of the OP? Commutator is some result of computation of this OP, but if you just remember how symmetries act. But, but you say this for the primary fields, right? Um, and I'm asking how to write this in general. So I want to say, well, actually, I'm writing it in a very bad way from the point of view of position of on the blackboard. But maybe it's fine. We'll do like this. So no, I want to say that it is the contour integral dz over dw over 2 pi t of t of t of w of just this t of w o v of z, because expansion of t of w o of z is sum of l n o of z over z minus over w minus z to n plus 2. So if n equals to -1, we need to take just a first order pole. So it is not this integral. And we also know that since L-1 corresponds to translation, then a transformation of any field under translation is given by its derivative. So this OP of T of W with O of Z always has a derivative of O at order W minus Z. So it is the integral of d W over 2 pi I L minus 1 O V of Z over O of Z over W minus Z plus some higher terms in principle and plus some lower terms. No, but lower terms are regular, but we can write them anyway. So this equals to derivative. Sorry, I wanted to write this derivative now. So it will be d all of that. Well, it is true for all fields, not necessarily for primaries. So it gives d O v of z. Right? So L minus 1 acts by derivative. Okay, but now if we say that our field has a dimension 0, it means that correlators with this field do not depend on coordinate. And in principle, if we work in the unitary theory, this field should be identified with identity operator. But even without this identification, if you have some topological operators, you have something that does not depend on coordinate. So if delta equals to 0, then this then d O delta equals to 0. D O 0 equals to 0. and this is so it's some common sense restriction, and this is consistent with the statement that L minus 1 minus 1 on 0 should equal to 0, which is precisely achieved by factorization by this submodule. So is it fine? We can also compute a different thing. We can look at this from the point of view of a scalar product. So we have this state L minus 1 of 0, and let us compute its norm. Actually, there is a question about how to compute conjugate states, but probably we discussed it already. So maybe I'll ask, is it clear how to write the norm of this L minus 1 on a vacuum? So should be a scalar product of the state with itself. So is it clear how to write it as a matrix element? But no, it is in the it is in the plus integral formalism, right? But I want to use a more abstract definition, saying that scalar product is just a correlator of two states at 0 and at infinity. So. Yes, and so if you want a scalar product of two vectors, so let's postpone this computation. So scalar product of two vectors, some v and w is this pairing between a Brown-Cat vector. The question is how to move Virasoro generators from one state to another one. Yes. 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 So if we have L minus K here, then it equals to LK here. Because in this case it is written as the integral dz z to k plus 1 or maybe better to write this expansion of t of z. So here we have an expansion dz squared t of L k Ln over z to n plus 2. Here we can expand it around infinity, and it will be an expansion d1 over z squared L minus n over 1 over z to n plus 2. So we have an equality of these expansions. So one can be used around z equals to 0 to compute the action of L of L minus k here, and another one can be used to compute this action. So
Here you're using the fact that when you have an index square, it becomes complementary.
yes. Yes, it is just easier to write this formulas in this form because if you try to write that there is some t and t tilde and you need to multiply by Jacobian, it is 1/2 probability that you divide instead of multiplying. Okay, so there is this a scalar product defined in this way. So basically it says that Lk dagger equals to L minus k. And it is just bilinear without any complex conjugations.
So why here the data is with respect to a well-defined permutation metric, or it's just a way to write it to make it make sense within this bracket?
Also, it's not a Hermitian in a sense, it's a complex valued. So probably the name is, I don't know if it is applicable in this context. It's kind of a Schrader scalar product, which is defined just as a correlator of a pair of fields. So this dagger is a complex linear operation. It doesn't have any complex conjugation.
Okay, so you take LK as a
Oh, so it just says that, so we know this formula that if we move LK from one place in the scalar product to another one, it flips sign. But by definition, this procedure defines a conjugate operator.
okay, so it's just a conjugate. It's the permutation conjugate is just a symbol.
Yes. So it's more like transposed actually, because it is a real metric. It's a real sense complex valued. Okay, so actually we can continue this computation here. So this will be 0, L1, L minus 1, 0, right? And, what does it equal to? Mm-hmm. Mm-hmm. Yes. So, hmm? No, it's a scalar product. Ah, yes, yes. So, or in other words, we have the following situation. There is this module that corresponds to a state of dimension 0, and we know that this scalar product can be diagonalized because it is some quadratic form. So now this vector is orthogonal to everything else, we have just defined the scalar product in this way. And now we are checking what is its norm. And we find that it is 0, which means that a correlator of any other states with this one, with this operator, will be 0. Um, so we can, of course, say that we have such state in the Hilbert space, but it will be state of zero norm that does not contribute to any correlator. So. So the only state which could give zero correlator was this state itself, but we computed that its norm is 0, so it vanishes under all correlators. And there is a reason to say that it is 0 in this Virasoro representation. So.
This is similar to what one does in quantum electrodynamics when one pushes out the interspace by the null.
That correspond to gauge transformations.
Yes.
Is it similar? This maybe. Maybe so maybe it is similar in the sense that we remove states of zero norm, but I don't know if it is similar on some deeper level. In a sense, if we can try to interpret this as some gauge-like symmetry. So it is related to this translation symmetry, that we have some state which is invariant under translations, and we remove it. But I don't know what is the different meaning of this. And technically, it is just a statement that a derivative of identity operator is 0, and so we remove it. And so are there any other questions about this? And in general, we can check the following: that probably I can erase this. So here, so what that there is some submodule in the Varma module, and it's so its highest vector has zero norm. But there is also a more general statement that any submodule in this Varma module is orthogonal to everything. So how to check this? So this submodule has some highest vector, let us say chi. Is chi highest weight vector, another highest weight vector. And let us say that L0 on the sky acts by some n plus delta. So it is some submodule somewhere. There is nth level, and there is this vector chi, which generates another module. And there is this vector chi. So in principle, so is it clear that different levels of this Virasoro module are orthogonal? So let's say that yes. So we can say that this VC delta is a direct sum of VC delta n's, so that L0 acts by n. Well, how to write this? Sorry. Restriction of L0 on this equals to delta plus n. And statement is that we see delta n is orthogonal to V C delta m from m different from n. So
Aren't those B, C, and all nested in each other?
what do you mean?
Like,
No, these are just different weight components. So from n equals to 0 to infinity.
yes,
Like
for example, the n equal to the component is just equal space, no?
no, n equals 0 is this single vector.
Ah, okay.
So it's just a expansion with respect to this L0 weight, V2, and so on. We simply compute L0 V n with W m. So so it equals to V n L0 WM, right? And on one side, this equals to n plus delta. And this equals to n plus delta. right? So it should equal to 0 if n is different from m. It just because L0 is yes, L0 is some Hermitian operator, and it is a statement that its eigenspaces with different eigenvalues are orthogonal. Yes, especially this argument. Mm. So these components are orthogonal. And also technically, we can get this just by moving this else through each other. We have different number of positive and negative else, so we'll get either positive or either negative else, which kill one of the two vacuums. But so there are different ways to check this. Yeah. Let us now use it in this case. So this vector chi is at some level n. And so it can have non-trivial scalar products only on the same level. And let us compute the scalar product. So some vector delta L minus L1, L minus Lm. Oh, sorry, plus, because it acts on the left, on chi. So a sum of, so L1 plus and so on plus Lm should equal to n, because it is it should be on the same level. And what does it equal to? Yeah. Mm-hmm. Yes. So this is orthogonal to all vectors in the submodule. And if we now try to compute the commutator of any descendant of chi, so we have this already. And for any for any descendant, we can do the same. By the way, I forgot to say that this is called so on the in the operator language it is called a primary field, and this states are called descendants. Okay, so for descendants. So we will have some delta L, L1, Lm, some L minus P1, P M L minus Pk echelon chi, and this so the number of this L's, so their total weight is plus Lm. This equals to so first let's write for this P1 plus Pk. So let us say that it is descendant at a level R. And here it is descendant on level r plus n. So, what will be the what will be this scalar product? Hmm? Could you say it again?
The left vector is some BC r plus n, and the right vector is some BC r.
Well, you can say it this way because it is a kind of submodule in this module. So effectively, yes, they lie on in different gradients of different modules, although which live in the same gradient in this bigger module. But technically, yes, it is the same computation. We can say that this equals to 0 because it can be kind of reduced to the scalar product, which is 0. Or we can simply say that the total that sum of indices of this else is different, and when we move all the cells to the right and all this else to the left, will not get any L0 or C, because so we will always end up with some positive or negative else. In this case with positive else, and it will vanish because of this. Well, the problem with the argument about this orthogonality is that in principle, if we try to use this action of L0, we need to no, let me think.
So this one to be 1 plus n and the other n. Then delta in chi differ from 1 differ by 1.
Oh,
Then they have 0 and the value is the same. No.
So So we should somehow use the knowledge about chi and the fact that its product with all such states is 0. Mm-hmm. Yes. Yes. And so it will contain else with non-zero with a non-zero sum of indices, because Virasoro relation, which I removed already. No, we can also say that this operator. So there is some operator between these two vectors, and its commutator with L0 is non-zero. This operator has non-zero weight, right? So we can say that. So let us say that there is some operator A, and a commutator of L0 with A is what? No, because you see the number of these L's is r plus n, because and the number of indices of this L is r, because this two vectors, and these two vectors should lie on the same level in the bigger Varma module. So basically the picture is this. And we have some vector which is at some module at some level r in this module, and so it is at the level r plus n in this bigger module.
So the difference of the combinator is just
Yes, so minus n, I think, because minus n a. So it means that when we move all positive L's to the right and all negative L's to the left, we will be left with some number of positive L's, because uh, so so this operator can be written as uh, some sum uh, of L and one and one. Well, let us reorder them. L minus p1 prime, L minus p something prime, L with L1 prime, p k k prime, L m prime prime, some sum of this form, and such that at least some of these L's are non-zero, because we should satisfy this property. So, so really, is it fine? Yeah. Well, maybe it can be said in some better way. Mm. Hmm? Mm-hmm. Yes, yes. Hmm. Oh, oh, if it was some well, yeah, yes, it's true. Yes. Mm-hmm. Yes, yes. Maybe it is even simpler. Yeah, thanks. But But we cannot get L0 alone because of this commutator.
So
Hmm?
the argument on the right was that if we take two vectors with different eigenvalue with respect to n0, they're your problem.
Yes.
Then chi has eigenvalues n plus delta, and delta has eigenvalue delta.
Yes.
Then if we add with some else, the eigenvalue of the L acting on x becomes delta.
L acting on what?
Why?
Hmm?
Because one is the R descendant of chi, and the other one is the R plus n descendant of the.
Before the line above.
Which one?
Delta with L and 1 and n chi.
That's before the one way. So it's hit by your.
So weights of these two vectors are the same. Because otherwise it would be zero because of this argument, because they both lie in this big Varma module. So so it would be zero because of that argument. But if we now write a descendant of delta, which could give some trivial scalar product with chi, it becomes zero because chi is the highest vector. So and it is so probably it would be possible to somehow define this zero scalar product between a submodule and and a big module, but in a sense, probably this argument could be made cleaner, but I don't know. Does it now look obvious or not? So does it look obvious now that these vectors are really orthogonal? Okay. Okay. So the point of this is that from our point of view, this submodules in the Virasoro module should better be removed. So and also if we know from some other sources that representation of the Virasoro algebra that we have is unitary. In a sense, it does not have vectors of zero norm. It means that all such states, all such Varma submodules are automatically factored out. So. For example, we know this in this case of free boson, because we can compute the scalar products of all states in the Heisenberg module, and so this J is for different terms commute, and if you compute scalar product, it will be zero if there are two different states, and some negative number if it is in the same state. So we know that this H alpha is some unitary representation of the Virasoro, and so for general alpha, if we know that this Virasoro submodule is irreducible, then we know that it is isomorphic to this Heisenberg module. But if we go to some special values, then we will know that it is something which has the same character as Virasoro Varma module. But if Varma module is not irreducible, it means that there will be no vectors. The states are also called null vectors. Like what to say? So there will be some module that contains null vectors. We should factorize by these submodules, but since the character is the same, it will mean that there are some other submodules which are orthogonal, of course, to that one with some different highest vectors. And in principle, for example, for alpha equals to 0, there is an infinite combination of these reducible Virasoro representations. In a sense that some of them are factorized by submodules, and some new submodules are inserted, then some new modules, new irreducible modules are inserted instead of them. But we'll look at such things probably next times. In a sense, we'll study a structure of some special representations. So, are there any questions about this? Mm-hmm. In the same way, it's trace of Q to L0. Yes. And we know that this J is also raise the value of L0 by n. Yes, and J minus n raises eigenvalue of L0 by n. Then we can do the same computation. Being completely sure that all these vectors are linear independent.
Way to write the full Hilbert space, which is in terms of this box space with respect to vertices, and the other one is with Zeno modules, or Zeno modules without these submodules.
Yes. So we have this Hilbert space defined as this free boson Hilbert space as this Fock module, and then we can take this Virasoro algebra, start acting on it, and see how it decomposes into this Virasoro reducible submodules.
Are the two things compatible?
What do you mean?
So, for example, for some alphas, H alpha splits as some representation of the Virasoro.
Yes, it will happen. And there will be several representations of the Virasoro. Also, so for example, if you take alpha equals to 0, we already know that in this case there will be L minus 1 acting on 0, which is orthogonal to everything. And since this representation is unitary, it will mean that it just identically 0. If we write Virasoro realization in terms of this free boson.
So in this case, H0 is the same as n vacuum 0.
No, because M vacuum 0 has a smaller character. It does not contain this part. It means that we will have another submodule that replaces this factored out part.
So just from looking at the characters, you could say that there is a submodule.
If you know that some representation is actually reducible, and you know that that one consists only of irreducible representation, then of course you will see immediately that. Yeah. But in that case, so this is this first approximation to this vacuum module. In a sense, this should be factored out always for any C. But this C equals 1 is special, and it is a result of this speciality that this representation will not be irreducible also. So we will need to factor out more vectors. actually there will be some infinite number of such vectors that should be removed and then replaced by other submodules. Okay, so any other questions? Hmm? All null vectors actually equal to 0 in H alpha because they are because this is a unitary representation with a positive definite scalar product.
So alpha equals to 0,
No, we get the same character, but if so originally it was just a single Varma module, but if this Varma module gets some null vectors, they vanish identically. But instead of them, we have some new highest vectors that belong to different Varma modules. So, okay. Yes. Well, actually, composed of this factorized Varma modules in irreducible representations.
the zero vector with multiplicity.
No, could you, no,
The character should be the same. I mean, if I say all null vectors are 0,
yes, but so it looks in the following ways. So originally we had this so alpha generic. We have this Verma module. When alpha equals to 0, we get a module without this.
I see.
But this is so it simply means that so originally there was this single state and it could be obtained by the action of L minus 1. But now L minus 1 acts by 0. So let me write this state. Actually, it's better to write the formulas for action of this Virasoro. And probably we have a little bit of time. So here it was alpha. Here it was j minus 1 alpha. Which was proportional to L minus 1 alpha. Let us actually write the formula for this else. We have T of z equals to 1/2 normal log n of g of z squared, which means that Ln's equal to normally ordered sum. Let me write L minus 1. L0, J0, J minus 1 plus, no, let me write it in this way, sum for J n, J minus 1 minus n, from n equals to 0 to infinity. Maybe, oh, it doesn't matter. In particular, it contains J0, J minus 1. Right? Plus everything else. So if we act with this vector on the highest weight on this highest vector, it will contain, let me write L minus 1 acting on alpha equals to alpha J minus 1 acting on alpha. Right? So when alpha equals to 0, it acts just by 0. So, but this vector is still in this module. So we have this vector. So plus something that grows from j minus 1 alpha, j minus 1 0. And actually, there will be also some modules here that should be removed. So there will be some infinite sum in this case.
So you said that H0 in this case splits in the same way as BC0 or B1 0.
Oh, in the sense that all these submodules that disappear from VC0 should be replaced by some direct summons. So in the Varma module itself does not does not have this direct sum representation, because there is a submodule, but its vectors are obtained from the highest vector. So there is an inclusion, but there is no inverse map from the Varma module to this submodule. And so there is only this exact sequence, but we cannot say that VC0 equals to VC1 plus M M vacuum C. So, in a sense, originally we have VC0, and when we go to some special point and we know that everything is unitary, we get this combination. So these objects have the same character, but different structure as representations of Virasoro. So one is this extension for general dimension. Another is this direct sum of. Is it clear or not? Probably there can be some analogy that in the general situation, all these operators can be described by matrices of this shape. Let me think. With 0 here. In a sense, these matrices have invariant subspace which corresponds to this submodule, but representation. No, it's a bad analogy.
It's not decomposable.
Yes, so this representation is not decomposable, which we have for generic alpha, and for the special value of alpha, this matrix elements vanish, and we get direct sum. Actually, I do not compute this matrices explicitly, but I think it should be something of this kind. Okay. Are there any other questions? So last thing which I wanted to tell is the interpretation of this character of the vacuum module. So we have this module, and L minus 1 acting on vacuum equals to 0. So and the question is, who is L minus 2 acting on 0? So what field does it correspond to? Yeah, thanks. And well, in principle, we can. What happens if we insert here some derivative? So what is the action of a single derivative of single L minus 1? Hmm? Yes. So, and if you insert k of them, there will be case derivative of t, right? But can we compute it in some other way using commutation relations in the Virasoro algebra? So what will it be? What state will it be? So a reminder that Ln equals to C over 12 n square n cubed minus n plus n minus m L n plus m. Yes, and then so L minus k minus 2, right? Because L minus 1 acting on 0 is 0. So so we see this mapping that L minus 2 corresponds to case derivative of t, and L minus 2 corresponds to t, or all other L's correspond to case derivatives of t. Hmm? Why? Because L minus 1. Okay. Yes, with some per factor. It's true. But let us just write that it is some prefactor. K factorial maybe or not. K. Hmm? Ah, no. Let us just say that it is some factor. Since I'm interested only in the in the type of factor we get. Uh, so we have this correspondence, and if so now we can ask about all other states, in the sense what kind of fields do they correspond to. So maybe. Or maybe let us talk about the definition of regular product in CFT later, because it is another not very small topic. But what I wanted to say that in principle, if you have such fields, we can multiply them. And we can have something like t to m1 dt to m2. Maybe let's write that it is m2, m3, d2, t to m4, and so on. So there are such fields, all m2, m3 to infinity. And you see that the number of such fields is precisely equal to this character. So, these fields that are normally ordered differential polynomials of an energy momentum tensor are precisely the fields from this vacuum module.
So, independent ways you can create an operator with
yes. So we see this operator. We see this operator of correspondence in action. So we did some algebraic computation, realized the derivative x by 0, so minus 1 x by 0, and but on the other side, other side, we can just count the number of differential polynomials of some field of dimension 2. And it is consistent. And if we have some other theory with some special central charge, it can happen that some of these differential polynomials also vanish. There are some relations on T of z. Okay, so are there any questions about this? Yes, by the same character, because a dimension of t is 2, and this corresponds to this first factor, and dimension of dt is 3, and we can have arbitrary powers of them. And this fields actually can correspond to suitably chosen regular products in CFT, because they correspond to states with some number of cells acting on vacuum, and these actions will actually correspond to regular products. So but I will discuss it later. So this vacuum module is a kind of so vacuum module on the operator side is the vertex operator algebra constructed only from the energy momentum tensor. So we don't use any other fields, just take t and its derivatives and construct everything we can. So, any questions about this?
How do we use the factor count
No, we know that character already, and I'm saying that we can count the number of the separators precisely in the same way. That a power of t can be arbitrary, a power of dt can be arbitrary, and we compute the same sum. But now it is just sum. Is it written somewhere? No, it's already erased. So we are computing sum over uh, uh, so we are computing sum over m2 equals to 0, m3 equals to 0, and so on to infinity of q to 2m2 plus 3m3 plus 4m4 plus and so on. And it equals to 1 over product of 1 minus q to the k from k equals to 2 from k equals to 2 to infinity. Yes, and it can be also checked in other way. So we need to say precisely what is the meaning of this product, and so we can literally construct this map. And so the way to compute this character is a little bit different. Here we just said that the first field has dimension 2, and so we take product from k equals to 2. And in that case, we said that it is a difference of 2 characters, of 2 Verma modules. Okay. Oh, yeah. Any other questions? Okay, so see you the next week. Yes.